Hey everybody, welcome back. I want to have a look at something going in a different direction now. Previously, we have seen one particular example of where needs in other disciplines, in this particular case, the very general thing of being able to collect and access information, has inspired advances in computer science, in this case the World Wide Web, which of course you're using at the moment to access this video and the materials related to it. Now I want to have a look at the other direction and see where advances in computer science and computer science research have inspired changes in other disciplines, in particular have enabled better science and more exciting science in other areas. And the thing that stands out to me there are computational simulations. Computers are obviously really good at computing things, and that's where the name comes from. And that allows us to do things that we were not able to do before, in particular in the context of science, simulate how something might behave in a different context without having to actually build it or without having to change a very complex system and then observe what happens there. There are many advantages to that. The obvious advantage is that I don't need to build a physical thing and then maybe break it in an experiment. So for the next experiment, I have to rebuild it or build something different from scratch or something like that. In a computational simulation, I don't have these issues. Another advantage of this is that I can measure all kinds of things that maybe in the physical world are very difficult to measure, because I can, for example, simulate a fire and then look inside and what happens where the fire is. But in practice, you probably don't want to do that, right? Because even if you can build the thing and set it on fire, you don't want to be inside the fire. So computational simulations allow us to do things that we were not able to do before and observe things with greater precision and gather more information about the things that happen. That also applies to things that otherwise we would not really be able to investigate at all, like the Earth and planetary systems in general. We can't easily go to other planets, and we cannot easily change what happens on Earth on a large scale, but in computational simulations, we can. We can build an Earth, and we can then simulate, well, what happens if the temperature were 10 degrees higher, for example, and based on the results of such a simulation, come to all kinds of conclusions about what we should be doing or what we should not be doing. Similarly, we can simulate planetary systems and see what happens if we shoot a spacecraft towards Mars like that, rather than actually having to do this, which is obviously a very difficult and expensive undertaking. And now I want to get into a little bit more detail as one particular example of a computational simulation about climate and weather models, because this is really something that we weren't able to do before in the same way before the advent of computers. Of course, you could predict the weather, you could have a look at the clouds, and maybe you could phone a friend who lived 100 miles away and they would have a look at the clouds, and then you could come to some conclusion about whether it would rain tomorrow or not, but not really with the same accuracy and the same level of detail that computational simulations allow us to do this today. And for this, I want you to have a look at a very short video linked in the resources for this video here, giving you a little bit of an introduction to a climate model that is developed and maintained at NCAR, just south of here in Boulder, Colorado. And the particular reason that I chose this video is because you get a very short glimpse of the computational hardware that the researchers are using to run these simulations and to to develop their climate models. That hardware is actually based in Wyoming, near Cheyenne, and that is one of the big investments that national agencies have made in Wyoming and also the state of Wyoming. So have a look at that, get a little bit of a better understanding for these particular types of models. And then once you've done that, there's another hands-on exercise that might be fun to take back into the classroom and have your students do, and that is to play around with a web-based climate model that allows you to explore a couple of different scenarios. You can find the link to that in the resources for this video, and we will have a very brief look at this right now. So it looks like this here. It's a website, and okay, it's a scientific website, so it's not particularly flashy, but it gives you access to all of the things that you need here. You can, for example, have a look at different climate change scenarios. Here's one particular scenario. You can find more information on that on this website, but this essentially gives you the results of a simulation here, where over time you can see how the surface temperature in different areas of the planet and at different times of the year changes. You can change the scenario here and choose one of the other ones, for example, solar obliquity axis tilt, and this will then show you the results of another simulation here, so you can explore a couple of different scenarios, see how things change and how the computational simulations say it would change based on different input scenarios here. All right, have a look at that. And like I said, this might be a fun exercise to take back to the classroom as well and have your student explore different things that are enabled by computational simulations.